A very warm and cozy good morning, everybody. Let's, without any much ado, begin the topic of today, which concerns with something that we have already covered before. Then why am I doing this again? Well, if you remember, while learning sets, we had also dealt with the different varieties of sets. If you remember, we had dealt with empty set, we dealt with singleton sets, finite sets, infinite sets, power set, universal set, so many sets. And therefore, it was a task to basically classify the set we have into any one of those categories and then deal with it. Similarly, after learning sets, we move on to learning relations. And therefore, it is a very intuitive question to ask whether we have in picture the different varieties of relations or not. And the answer to this query is that yes, we do have different types of relations, but relations not from A to B, but different types of relations from a set to the same set. What I'm trying to say is there are types of relations from a set, suppose the set A, to the same set. That means I can also say I am going to teach you the different types of relations on A. Here the categories of different relations do not come when we have two distinct sets in picture. The entire topic is going to deal with the different classes or different varieties of relations when both the sets, the first and the second set, are the same. The very recent topic that we have studied is relations on a set. And it is this topic which concerns this particular topic in continuation. And therefore, let me bring before you the different varieties of relations from a set to itself. The very first category deals with a very nice kind of a relation. What is the name of this relation and why is that name kept? All these queries are going to fetch answers just after this slight example. Let me give you a set A, which is suppose 1, 2 and 3. What I am seeking for is a relation from a set to the same set. That is why I am not going to give you another set B over here. The only set which is going to come into picture is the same set A. And therefore, the role of both the sets in the Cartesian product is played by the single set A in this particular topic because we are dealing with relations on A. Therefore, after this, I am concerned with basically the relation which is going to act on this set. And therefore, the relation in this example is described as the collection of all those ordered pairs x, y belonging to the Cartesian product of A with itself such that what is it that they satisfy? The rule which is governing the existence of members in the set R says that the difference between both the components of the ordered pair should be exactly equal to 12. And one more very slight observation to be noted is that this x and this y coming from the Cartesian product of A cross A itself basically ensures that the first element small x comes from the first set A and the second element small y also comes from set A because set A itself is the second set. But just for another time remembrance, I am going to write that both x and y should come from the set A. That means inside the set R are those ordered pairs of A cross A which satisfy the rule that the difference between the first and the second components should be exactly equal to 12. And now is the turn to unveil the very members which sit inside R. I told you in the last lecture also, it is always advisable to understand the set builder form of this R and then convert it into the roster form, because then only can we actually see the members and conclude about their properties. Now that I am searching those members of the set A cross A which satisfy this rule, first of all, I will have to make my set A cross A. Because the moment I make the set A cross A, I will be left with the exercise to pick up members from A cross A which satisfy this rule and hence get this R in roster form to be a subset of A cross A. Therefore, without much ado, let's start finding out the members sitting in the set A cross A when the set A is just 1, 2 and 3. You know that with the arrow diagram technique, how do we find the set A cross A? It's very easy, we've done it umpteen number of times. In both the Venn diagrams, I am writing A itself because A is the first set and A is the second set as well. Now I am going to jot down the members of A inside this Venn diagram. A has members 1, 2 and 3. Here also I am going to write the same members. I am interested in the Cartesian product of these two sets. That means I have to find out all the ordered pairs A, B such that the first element small a comes from the first set capital A and the second element small b also comes from capital A. That means all possible ordered pairs with the two components coming from A itself. And the very smart and easy technique is the arrow diagram technique, which is from each element of the first set, draw arrows to each element of the second set. Pick up the first element of the first set, which is 1, and start drawing arrows to each element of the second set, which is again A. That means from 1 I'll have an arrow going to 1, from 1 I'll have an arrow going to 2, from 1 I'll have an arrow going to 3. Thereby giving me 3 distinct arrows from 1 to 1, from 1 to 2 and from 1 to 3. Similarly, because the statement of the arrow diagram technique says that from each element of the first set, draw arrows to each element of the second set, so the second element of the first set too is going to do the same thing. That is, it is going to go and pair itself up with each element of the second set, thereby giving me 3 distinct arrows again. Moving to the last element of the first set, which is 3, I want this 3 to pair itself up with every element of the second set. And that pairing through arrow diagram is shown by the arrows. You start with the number 3, the arrow, and end the arrow at each of these numbers in set A, thereby giving you again 3 distinct arrows from 3 to 1, from 3 to 2 and from 3 to 3, which is the last element of the second set. This way, all these arrows basically show you all the possibilities in which you can pair up 2 components of the same set A. That means all these arrows, basically 9 arrows in number, through their starting and ending points, give us the 9 distinct ordered pairs with first element from the first set and second element from the second set. And that's it. Mind it, not just these 9 arrows will give us 9 elements, but these are the only 9 elements which are sitting in the set A cross A. No more arrows, no more members. Each member is going to come corresponding to an arrow, and each arrow is going to correspond to a member. No more arrows, no more members, 9 distinct arrows, 9 distinct members in the set A cross A. And what are they? Well, we know I'm not going to list them down because corresponding to 1, I have 1, 1, 1, 2 and 1, 3. That's it. That means what I want to stress on is, if your x is equal to 1, that means small x, the ordered pair x, y, if your small x is 1, the 3 ordered pairs with this 1 as the first element inside A cross A are 1, 1, 1, 2 and 1, 3. All these members are members of A cross A with 1 as their first element. Because there are only 3 arrows starting from 1, these are the only 3 ordered pairs with first element 1 sitting in the set A cross A. Let's do the analysis with small x equal to 1 over here. What I want to do the analysis of is that among these 3 members of A cross A, is there any member which satisfies the rule that x minus y is equal to 12? Does it? Does these members satisfy this rule? Let's go and check. Well, with x equal to 1, the very first possibility, what I want is, I want a y such that x minus y is equal to 12, so that I can put that x, y ordered pair inside the set R and get R's members, because that is what I want to find. I want to find the roster form of R. That means I want to find all the members which qualify to sit inside R. Therefore, corresponding to x equal to 1, what is that y which is going to give me that x minus y is equal to 12? Let's find out. If x is equal to 1 and you want that x minus y should be equal to 12, this means you want 1 minus y is equal to 12. Isn't it? You definitely want this because x is equal to 1. And this means y goes that side, you get 1 minus 12 is equal to y, which means y is minus 11. Corresponding to x equal to 1, the y which satisfies the rule of x minus y equal to 12 is y equal to minus 11. And that is why the ordered pair corresponding to this x and this y comes out to be 1, minus 11. Just try and see if the rule is verified. I want x minus y to be equal to 12. So small x is 1, your small y is minus 11. When you subtract 1 minus 11, 1 minus minus 11, it comes out to be 1 plus 11, which is 12. And that is why we have done a very smart approach. We found out y only if it satisfied the rule, and therefore it's obvious that 1 minus 11 is definitely going to satisfy the rule of x minus y is equal to 12. Just because this ordered pair satisfies the rule of x minus y equal to 12, am I going to pick this up and place it inside the set R? Am I allowed to do this? Well, inside the set R are those ordered pairs which firstly should come from A cross A. That means only those ordered pairs which can be picked up from A cross A, and they should satisfy this rule. So, yes, 1 minus 11 does satisfy the rule, but does 1 minus 11 belong to A cross A? Let's check. The only members with 1 as the first element which belong to A cross A are 1, 1, 1, 2 and 1, 3. That's it. there is no 1 comma minus 11 coming from A cross A. And if there is no 1 comma minus 11 in A cross A, how can I pick up 1 comma minus 11 from A cross A and put it inside R? And that is why even if the rule is satisfied, complete statement of the rule is not satisfied. Therefore, 1 comma minus 11 is not going to come inside the set R. Similarly, if I go to study the next 3 arrows emerging from 2, all these 3 arrows basically give me another 3 ordered pairs with first element as 2, second element as 1, first element as 2, second element as 2, first element as 2 and second element as 3. These are the members which belong to A cross A corresponding to these 3 arrows, and they are the only 3 ordered pairs with 2 as the first element. Therefore, if I want to find out which among these 3 ordered pairs makes its position inside the set R, I will have to start with the analysis. So, if I take x equal to 2 and I know that x minus y is equal to 12 is my rule, I am in a search that corresponding to x equal to 2, which is that y which is going to make me satisfy the rule of x minus y equals 12. And therefore, with this particular x, the rule becomes 2 minus y equals to 12. Which means y goes that side, you get 2 minus 12, which gives you minus 10. Corresponding to x equal to 2, you have got y equal to minus 10. And therefore, the ordered pair in picture is 2 comma minus 10. You can verify 2 minus minus 10, which is 2 plus 10, is giving you 12. So, corresponding to 2, the ordered pair which satisfies the rule of x minus y equals 12 is the ordered pair 2 comma minus 10. But can I place it inside R? Again, the problem lies that the y which is being obtained here, which is equal to minus 10, does not come from set A. That is why there is no tuple like 2 comma minus 10 here in the list. The only members of A cross A with 2 as the first element are 2 comma 1, 2 comma 2 and 2 comma 3. Nowhere it is 2 comma minus 10 because there is no minus 10 in the second set, and in the ordered pairs, second elements always come from the second set. That is why I cannot borrow 2 comma minus 10 from A cross A because A cross A doesn't have 2 comma minus 10, and therefore this member also doesn't make its place inside R. Going to study the last 3 arrows emerging from the number 3 correspond to giving me again 3 distinct ordered pairs with 3 as the first element, namely 3 comma 1, 3 comma 2 and 3 comma 3. These are the members which sit inside A cross A, thereby completing the list of 9 members in A cross A with 3 as the very first element. That's it. Only 3 ordered pairs are there with 3 as the first element. Therefore, if I want to find out which among these 3 members makes its place inside R, I will have to again start doing the analysis with small x equal to 3, which is the first element. And therefore, if I take small x equal to 3 and I want the rule to be satisfied by a some certain y, this means I want there should be a y in picture such that 3 minus y is equal to 12. Right? And therefore, once you simplify it, what is it that you get? You get y equals minus 9. Corresponding to x equal to 3, the y which satisfies the rule of x minus y equals 12 is y equals minus 9. And therefore, the ordered pair which comes into picture happens to be 3 comma minus 9. You can see the rule is satisfied again because 3 minus minus 9, which is 3 plus 9, is equal to 12. So can I put this inside R again? For putting an ordered pair inside the set R, which is a subset of A cross A because it's a relation, therefore a subset of A cross A, I need to make R to be a part of A cross A. That means inside R can lie only those members which are borrowed from A cross A. Nowhere else I can pick up members and put it inside R if it is a subset of A cross A. That is why only members of A cross A which satisfy this rule are allowed to sit inside R. Okay? So this is an ordered pair which satisfies the rule, but it doesn't come from A cross A because from A cross A the members which have 3 as the first element are only these 3. Because -9 is nowhere in the second set, therefore 3, -9, even if it satisfies the rule of x minus y equals 12, does not come inside R. And that is why this also doesn't make its place in the set R. That is it. That means A cross A all in all had only 9 elements. Out of these 9 elements, there are exactly no elements which are being picked up and kept inside R. Which means there is no member in the set A cross A which is sitting inside the set R. But R is always a subset of A cross A. This means R has no members of A cross A because there are no members in A cross A which are satisfying this rule. Yes, there are arbitrarily many members which are satisfying this rule, but no members in A cross A which satisfy this rule. And that is why R has no members of A cross A. This is the reason why I am writing my R is an empty subset of A cross A because it contains no members of the set A cross A. This relation, which looked pretty nice in the beginning, when we tried to convert it in the roster form, no members came inside R from A cross A. And that is why the entire form of R turned into one single symbol of phi, which means R is an empty subset of A cross A. Why did I do such a relation? Why did empty set come into picture right here? I am going to tell you in the next section. But over here, you have to understand the analysis which I did and digest the entire study. The point to be noted in this example basically was that yes, I had all the members of A cross A available with me, but when I had this particular arrow diagram with me and I had the relation also with me, was there any member from set A which was related to another member of set A with that particular relation? If it would have been the case that there would have been some member of A related to some member of A, I would have got that as a tuple sitting inside R. But there was no member of A related to another member of A, therefore R came out to be an empty set because no members satisfied that relation criteria sitting inside A cross A. What I am trying to say is the relation which I specified was of a certain type. That particular relation allowed no member of A to be related with any member of A. And that is why no two members which are related to each other by that relation could come inside R as an ordered pair. The name for such relations which don't allow any member of a set to be related to any other member of the same set is called void relations. Void relation is the name given to the relations which do not allow any member of the set to be related to any other member of the set by that particular relation. And therefore, let A be any set We already know this fact that the empty set phi is a subset of every set. Now A was an arbitrary set and we know that empty set is a subset of every set, therefore empty set is a subset of A. Also, this means we are not concerned with subsets of a single set. We in this entire chapter are trying to establish relations between two objects, and that is why two objects correspond to an ordered pair which are members of the Cartesian product of two sets, and that is why we are completely concerned with subsets of the Cartesian product. But because we are doing relations on a set, I am concerned with the Cartesian product of a set with itself. Because empty set is a subset of every set, this means that always empty set is a subset of the Cartesian product of A with A. This is also an arbitrary set and therefore empty set is always a subset of A cross A. Which means, what is the meaning of subset of the Cartesian product of two sets? This means phi is a relation from A to the set A. Or I can also say the name attached to this, that phi is a relation on the set A. Such a relation on a set is what is called a void relation. So what do I mean by void relation? We know that empty set is also called a void set, also called a null set. Therefore, because empty set is a subset of A cross A always, that is why this empty relation or void relation from A to A always exists and comes into picture. And by the very logic, this particular relation means that no element of A is related to any other element of A. This means there are no two members in A cross A, that means no ordered pair in A cross A in which the two components are satisfying the rule specified by this relation. And when there are no members in A cross A which satisfy this relation, in that case no members come and sit inside the set R, which is a subset of A cross A. And in this case, what you obtain is a void or an empty relation wherein it is a guarantee that nothing comes inside the set R, which is a subset of A cross A. After we have accomplished the concept of void relation, let's move to the next concept. And that next concept, giving you the second category of relations, is going to be clear again with a certain example. Suppose I take again the same set, which is 1, 2, 3, and again because we are studying A cross A, therefore I am not going to give you another set B in picture. Rather, suppose I give you the description of the relation, which is inside it lie all those ordered pairs of A cross A such that what is it that they satisfy? They satisfy that the absolute value of x minus y should be greater than equal to 0, and obviously x and y should come from the set A, otherwise the ordered pair x comma y cannot come from A cross A. This is the description of R, and now it is time to decode what R is. So, for R to bring into picture, we again have to study the ordered pairs of A cross A. Inside A cross A, we have already dealt with the arrow diagram of A cross A. In this case also the same arrow diagram occurs. 3 arrows emerging from 1 corresponding to 3 distinct ordered pairs with 1 as the first element, 1, 1, 2 and 1, 3. Similarly, 3 distinct arrows emerging from 2, thereby giving me only 3 ordered pairs with 2 as the first element as 2, 1, 2, 2 and 2, 3. And the last were 3 distinct arrows emerging from 3, giving me 3 distinct arrows 3, 1, 3, 2 and 3, 3. These were the only 9 members which sat inside A cross A, with 3 members having 1 as the first element, 3 having 2 as the first element and 3 having 3 as the very first element. It's now time to verify which among these ordered pairs is qualified to sit inside the set R. Starting with x equal to 1, if I want a y such that absolute value of x minus y is greater than equal to 0, what is it that I want? Basically, let me start. For y equal to 1, that is the first y that I have, mod of x minus y or absolute value of x minus y happens to be absolute value of 1 minus 1, and that is 0. Of course 0 is allowed because R says inside me lie those ordered pairs whose absolute value of the difference is either 0 or greater than 0. So if x is 1 and I take y equal to 1, definitely mod of x minus y is 0, which is allowed, thereby giving me the ordered pair 1, 1. For y equals 2 and x remains as 1, I get mod of x minus y as mod of 1 minus 2, which is nothing but absolute value of minus 1. And whenever you have a negative quantity inside the absolute value, it converts itself into just the positive quantity, and therefore this is nothing but 1. And therefore, corresponding to x equal to 1 and y equal to 2, the mod of x minus y is coming out to be 1, which is strictly greater than 0. And therefore, this ordered pair is again satisfying the rule that the difference of x and y should be either strictly greater than 0 or equal to 0. So, because it is satisfying greater than 0 inequality, this means this ordered pair is also successful in satisfying the rule. Left with just one more y, which is equal to 3, we get mod of x minus y is equal to mod of 1 minus 3, which is mod of minus 2. Again, like the previous case, the absolute value symbol converts it to just 2, ignoring the minus sign, which is strictly greater than 0 quantity. And therefore, it is again satisfying the rule, thereby making the ordered pair 1, 3 also successful. Definitely, corresponding to x equal to 1, the only 3 ordered pairs are these 3 sitting in A cross A, and all these 3 ordered pairs are satisfying the rule which R is saying. Therefore, all of them are going to successfully go and sit inside the set R. Similarly, exactly in a similar manner, if you proceed with x equal to 2, the first element sitting in the ordered pairs, and you start with y equals 1, you are going to get mod of x minus y, which is mod of 2 minus 1, which is nothing but mod of 1. 1 is already positive. This is nothing but 1, which is strictly greater than 0, thereby giving you the ordered pair 2, 1, which is satisfying the rule. For y equals 2, you get mod of 2 minus 2, thereby giving you mod of 0, which is nothing but 0. And it is again allowed because the rule says either the difference should be 0 or strictly greater than 0. Therefore, giving you that the ordered pair 2, 2 is also satisfying the rule. Left with just one more y equals 3, you get mod of 2 minus 3, which is mod of minus 1, and then the mod sign is going to just take out 1 outside, which is strictly greater than 0, thereby giving you that the ordered pair 2, 3 is again satisfying the rule. This means there are just 3 ordered pairs inside A cross A with 2 as the first element, and all these 3 ordered pairs are satisfying the rule which R wants. Therefore, they are members of the set R. Why don't you try this out with x equal to 3 and try and see whether the 3 members in A cross A with 3 as the first element satisfy the rule or not. And I am going to bring the answer just right now in 5 minutes. Up till now, we have been successful in seeing that all the members of A cross A having 1 as the first element and 2 as the first element have been successful in satisfying the relation specified by R, and therefore have been successfully sitting inside R as members. The only task now left is to verify the third row members. That means when your x is equal to 3 and y is equal to 1, what happens in mod of x minus y, 3 minus 1, this is absolute value of 2. 2 is already positive. Just take out 2 outside, and this means that over here also the ordered pair x, y, 3, 1 is satisfying the rule which R wants. For y equal to 2, you get mod of 3 minus 2, which is mod of 1. Again, it's positive. Just take it outside. This is again strictly greater than 0. You can see it. And therefore, the ordered pair 3, 2 is again satisfying the rule successfully. Left with just one more member, mod of x minus y makes it mod of 3 minus 3, which is mod of 0, which is 0 itself. And this is again allowed because the rule said either mod of x minus y should be 0 or greater than 0, and therefore this implies that the ordered pair 3, 3 is also satisfying the rule. Among the available 3 ordered pairs in A cross A with 3 as the first element, all these 3 ordered pairs are successfully satisfying the rule which R is specifying. Therefore, all of them are making its place and position in the set R. We are done with verifying all the members of A cross A one by one. And we have understood that every member of A cross A is satisfying the rule specified by R. The conclusion happens to be as every member of the set A cross A satisfies the rule therefore x, y belonging to A cross A That means if an ordered pair belongs to A cross A, this implies that ordered pair is going to belong to R as well, because every ordered pair of A cross A is satisfying the rule, therefore making its position in R for every X and Y in the set A. And this means, by the very definition, if every element of A cross A is sitting inside R, this means A cross A is a subset of R. But we already know that R is a subset of A cross A, because R was a relation on A, and these two inequalities give me that R is equal to A cross A. This is where the discussion stops, because we have got how the relation looks. This relation, which exactly resembles the parent set, is the relation known as the universal relation. Whenever you have a relation which is that subset of the Cartesian product which is equal to the Cartesian product, that subset of A cross A is called the universal relation on A. And this particular R now has got the name that it is universal relation from the set A to the set A or on the set A. This is the second type of relation on a set, wherein from the first category we understood that no member of A was related to any member of A, because of which none of the members from A cross A were being carried down to set R, and therefore R had no members, it came out to be empty. Whereas in this particular type, we observed that every member of A was related to every other member of A, because of which every member of A cross A qualified to sit inside the set R, thereby making R to be exactly equal to A cross A, the largest set possible. R in this case has borrowed all the members from A cross A and thereby has become equal to A cross A. Whereas in the empty relation or the void relation, R could not borrow even a single member from A cross A, thereby having itself to be empty. I am going to present a formal discussion on universal relation in the next lecture. By then, you are advised to spend time with these two types of relations on a set and play with them as much as you can. Meet you next time. Goodbye.